Hi everyone, thanks for coming. I'm Ilyas, and I'm here for talking about autonomous driving and so how a car can drive autonomously. And more specifically, how Python is in the system and how can contribute to this task. We'll see two perspectives. One of the normal city cars and another one from the perspective of autonomous racing car. This because I maturated 2 years of experience in the FRT, the racing team of the University of Florence, part of the Formula SAE international competition. And this task is difficult, it's complex to reach this objective of making a car drive autonomously. And so, as always we do as software engineers, we have to divide this task in simpler tasks. And in this case, it's even more important because we have to divide the efficiency and the complexity critical points. And from the beginning, we have the perception module, where simply we have to take the data from the external world and process the data in information and from about what there is in the external world. Then we have to understand where we are, because it seems simple, but it is not to understand where the car is in that moment. In fact, there is this famous slogan from the last century about it wasn't related to cars, but I modified it a little bit. And it's the car knows where it is by knowing where it isn't. This because it's a nice formulation about how the algorithms of localization works. But this, of course, can apply to robots and any other kind of vehicle. And then, when we understood what there is and where we are, we have to calculate and plan the trajectory we want to do. And after that, we have to translate that abstract concept of target point, velocity, curvature. We have to translate it in real-world operations. For example, how much brake we have to press, how much acceleration we have to press in the car for reaching the target properties. And all of this is integrated in the system integration module that makes so that these components communicate between themselves. And from a technology's perspective, we have actually to divide two cases, because when we want to implement some tests at the beginning, we can just do everything in ROS, the robot operative system. But of course, we want to make some parts more efficient, and both from a computational perspective and also algorithmically. And more specifically on perception module and trajectory, because as we know, for example, there are many computer vision models that can solve this problem, but we'll talk later about that. And we are here in PyCon, and so we can see more a perspective of Python, but it doesn't mean that these interfaces, these modules can be implemented in any way we want with multipurpose language or other there is also RTOS or other frameworks. But if you're interested even in the control part, I suggest you this GitHub repository. But as you can see from the technologies, we will not talk here about specifically about control and system integration, but in case you're interested. And so in the perception module, actually, there is a strong standard, because YOLO is the main deep learning model that is used in this context, simply because the car goes in the high velocity, especially racing cars. And so in this context, we need the best ratio between object detection precision and also the speed of calculation. And YOLO is the best one for this kind of ratio. But nowadays, the standard is not only using YOLO, but also using LiDAR, so a simple radar that allows the car to find objects not by using a computer vision model, but these technologies. And nowadays, we can say that any company uses LiDAR as a standard and also YOLO or variations of it. But of course, we can solve this task with other kind of models. For example, image segmentation. The simplest is UNet, but it's of course slower. Or strangely, but even agents, because I've been in many conferences and talks in Berlin related to autonomous driving, and I can say that more than one person told me that in their companies they are building solution to perception using agents AI, so using an LLM. That I think that 1 year or two, any one of us here could say that's maybe impossible, because LLM is the peak of slowness related to deep learning models. But somehow someone is trying to solve this problem, putting the images in real time to the LLM and having a description of what is happening. And now I just want to say this briefly, because once I was in a restaurant in Florence with a friend. He's a front-end developer, and I showed him some of these programs. I'll show later even to you. And he asked me how these plots are useful to us. And this made me think that sometimes the way we interpret data, maybe even in obvious way, for example, showing it in a map, can be strange for other people not in the sector. And so everything that can be seen from the camera can also be interpreted in some way using matplotlib. And I'm saying this specifically because talking about trajectory, the first task we are solving is to calculate the local trajectory, because at the beginning we don't know anything of what there is farther away, and so we have to calculate a local trajectory. The simplest algorithm is pursuit, that just using these two parts of the algorithm, firstly identify the target, and then using different calculations, using distance on the target point or the wheelbase of the vehicle, and a specific function calculates this angle. And the alpha is pretty difficult to see it without an image. And now we'll see a test of this local trajectory. Because as I told before, we have also to test visually how can it work in different circuits. Now we'll see just a single example. And as you see, the right cones are yellow and the blue ones are in the left part. And this is a standard in the racing competitions. And this is useful information we can use for solve this problem. And the orange cones are the starting and also the end of the circuit. Information that we can use, for example, using computer vision to understand that the circuit is finally completed, and so we can stop the car. Or we can use, for example, SLAM from the for the localization module for understanding that we are where we started, and so the path is ended. And when we finished a circuit, there is the possibility that we have to do it more times, because there are different formats of the competition, and one of this one. And so in that moment, we have more data, and so we can calculate the global trajectory. Because just a simple example could be that when we have 100 meters of straight line with a local trajectory path planner, it's difficult to, we are not going to do max velocity because we don't know if after 20 meters of, we have to change direction. And so in the local trajectory path planner, we will never go to max velocity. In the global trajectory path planner, we are going to do so because we have all the data. And so we know that if we have 100 meters of straight line, we can go for a portion of it at maximum velocity, an advantage to not ignore. And there are, of course, different ways. The simplest is to just calculate central line. And as you can imagine, is suboptimal, is not the shortest, is not the fastest, but is the easiest. In fact, we'll see how to implement the central line solution. But then another simple way could be adding heuristics. And a simple one is, for example, late apex. Maybe if someone of you likes Formula 1 could see and understand well these kind of heuristics. And from this perspective, we are implementing pattern recognition algorithms because we have to understand that there are some kind of curves that we can exploit for having a better acceleration. And so these are very famous techniques. In fact, there is drivingfast.net if you want to see other kind of heuristics. This is another one famous for when we have two curvature curves in the same moment and how to use both of them. And another simple heuristic, even simpler, is just minimizing the curvature that in some cases it could be useful. But we are in 2025, and so machine learning is, even in this case, the best one in finding the best solution. And there are two approaches. The first one is supervised learning, training it with a data set of historical competitions of circuits in Formula 1, for example, or reinforcement learning in the case we don't have any data set. And so reinforcement learning can actually be used also for the local path planner, but in this case, it's even stronger. And with, of course, reward minimizing the time. It's important, not the shortest path, because as we saw before, it's not the same thing. And we saw that central line is the easiest. In fact, we saw, we'll see now how to implement it. First of all, we have to understand which problem could we have for solving these central line waypoints. And here there is just a simple representation with red cones and left cones. And here, a simple problem is having not a smooth path, because we have 4 waypoints, but the second one in red is incorrect waypoint because it creates a not smooth path. And so at the beginning, we have to make sure that there are not too many waypoints, too many draft waypoints, but to create the optimal numbers, so then we can fit a line on them. And of course, also the association kind of solution is not working because it could be one of the first thing we could think, but the cones are not in the same number. And so the solution is using some kind of triangulation, but which kind of triangulation? There are many with different conditions. And so, for example, in this case, we have 1, 2 AB cones, and 1 A2 is, it seems to be the correct triangle, but why? We have to understand why. So which are the conditions for creating a good algorithm? And the solution is just using Delaunay that maximizes the minimum angle. And this is useful because having a low angle, we make sure that the waypoints are okay in the correct number, but they are not to close. And so we can have a good ratio between having a good path and also the good number of waypoints. Now we'll see this algorithm in act with an example. And so we'll see in the same circuit of before, we can first of all calculate all the possible Delaunay triangles. And as I told before, we have to interpret this image because we know that this is our circuit. And so we have just to filter the triangles we don't need. And it's simply done by removing the triangles where the free cones are of the same color. And so filtering them, we have the internal triangles. And so each part of the triangle is used for calculating the central point. And so for having a more close perspective, each of these is a central point. And so now we have a draft of the waypoints, and we saw before we have a good number, but we have to fit a line of them because, of course, we need a precise target point that the car has to do. And again, the shortest path is not the fastest, and even it's not smooth. So in our context, we want a smooth path. And so the solution is given by SciPy library with just the method of B-spline that is made by a couple of SciPy methods. The first one is spline preparation. That's a SciPy method that allows us to create a parametric function that describes that line, and so the path. But we don't want a representation of the function. So in this way, it's like an equation, but represented as a parametric function. But we want to evaluate then this function in some coordinates that for having the same number between each waypoints, we can just use the numpy linspace for having, for example, 100 waypoints between each two main draft waypoints. And so even in this case, let's see the final example of a global circuit. As we saw before, we have the waypoints of before, but now we fit a line on them. And here we are also calculating the curvature. In fact, we are distinguishing the green waypoints and the red one depending on the curvature. And depending on the curvature, we later will calculate also the speed the car has to have in that specific point. And in case you want to personalize even more this SciPy function, you can just add some parameters, for example, changing smoothness or the weights that each draft waypoints have. And I have an economics student friend that once told me that potential resources are considered infinite, but we are in the real world, and so they are more than finite. And in fact, in this context, but always in software engineering, we have to find the best solution between running time of the program, the time we need for developing it, and the resources. And these two are not constant relation, because as you know, the paradox that the more software engineers you hire, the efficiency doesn't increase linearly. And so what can be optimized? Well, it's not nice to say maybe here, but a a solution could be using C++ for the perception and trajectory, for having a faster calculation of this deep learning model. But it's not what we would like to do. So what can really be optimized? One simple solution could be using NumPy, because we apply many methods on NumPy and the arrays. And so the just-in-time compilation is useful for having better performance. But in general, the easiest way at the end is using sensors and cameras that can see farther. And this is one way for having a better performance. And I hope this has been a useful and interesting introduction to autonomous driving. And thanks for everything.
Thank you very much for your talk. So you can post your question online. We don't have one at the moment. Do you have any question in the room? Yeah.
Yeah, thanks a lot. I don't know if it makes sense, or maybe it's too technical. I was wondering if you can reformulate the problem of finding the best path within the circuit as like I guess a partial differential equation problem or a calculus of variation problem.
Okay. Well, do you mean specifically of the local, of the global, or?
No, the global one, of course, the global one.
Okay. Well, there are, I think, solutions, yeah, but we have also to understand that when a car goes really fast, we have to implement the fastest solutions. And I think that solution is not used for the reason that it could be computationally too... but that kind of solution, we have to also to understand that could work well in the racing cars, but when we have also other kind of objects, it could be a problem. For example, because in the city cars, also we have the, for example, prediction model, where we have to find the position of the next elements, the external elements, for example, pedestrians. And so this is all other computation added.
Thank you. So we have a couple of questions online. Do you memorize the circuit between laps?
Yeah, in the moment a circuit is completed. As we saw here, this is the matplotlib representation, but yeah, all the cones are memorized. And in fact, we are going to do the global path planning, because we memorize it with, particularly we used also SLAM, for example. It could be a solution for creating the map that now we represent with matplotlib. So yeah, that's the correct way and the best way when we have to do more laps.
Thank you. The next one is, have you tested your simulation in the real world scenario?
Yes, we also tested in the real world. And in fact, one thing we could say is that why implementing the center line path when is suboptimal? That's simply because the path in the real world, at least in the context of racing cars, is not big. And so implementing much, better solution, but with weight from the computational perspective, it can improve for 2 meters or even less. But at the end, it's good, but it's also a cost for the team implementing better solutions. And so for this reason, testing in the real world is fundamental also for understanding what we should implement and should build.
Thank you. Next is, oh, okay, they keep switching, depends on people how they vote. Okay, it's possible to calculate the best curve using genetic generation considering the speed?
Okay. I think that genetic algorithms are can be a good solution, but the standard, at least as I know, for the global, at least, is more on the on other kind of deep learning models because are more generalized, and so for this reason, I'm sure there are this kind of solution, but personally, I didn't see them at this point, at this moment.
Thank you. Next one is, what's the average speed reached?
I mean, for the, at least for these kind of competitions, cars can go fast as, not as fast as Formula 1 car competitions, but over 150 kilometers per hour. So not as low.
Nice. I don't have any more questions online. Anyone? Okay.
Nice talk. And about the circuit. How is it mapped? Is only computer vision, or is there some information provided by the programmer?
Well,
external of the car and
okay, well, it depends on the format because in some formats the map is known, and in fact there are even famous and specific circuits that you can also find on Wikipedia. So pages just for a circuit, and so yeah, in that cases you can optimize the path as much as possible for that specific circuit. And this is what we do usually, yeah. But in general, we have to find a solution that can work everywhere. And so computer vision at the end is what we use for seeing the position of the cones.
Any more questions?
Stuff like that, because that actually changes the maximum speed. I was asking about the banking of the curve, because that changes the for each turn. The maximum speed also depends on the banking, because you need to avoid that the centrifugal force will drift you away.
Yeah, well, the fact is that in the racing, the competitions, these kind of competitions, there are many assumptions, and one of these is specifically this one, because you have to see this sector as, for example, Formula 1, where cars, or even in MotoGP, there aren't, you have a flat soil. Okay, at least for our assumption, as you saw before, I understand what you're saying, and I heard this thing many times. So I know that's a possibility that can happen, but at least for this moment, we are not too much giving interest on this specific point.
Thank you. I think there was one here, the last one.
Thanks for the talk. About the global trajectory approach, is it able to adapt in case there is maybe a temporary obstacle on the track?
Sorry, the obstacles?
Like a temporary obstacle on the track?
Yeah. Well, I'll go just a moment in a slide. This is the architecture of we saw before, and the fact is that this is the basic architecture. Of course, real companies, and specifically for city cars, there are even the double or the triple of these modules, and these are the ones that cannot be removed. What you're saying is part of the prediction module that is between localization and trajectory, because we have to predict where the object, the moving object, are going, and so understand their movement, for then calculating the trajectory. Well, you said that for the global, in our context, in the racing competition, we have just still objects. So for this reason, we are not taking in account moving objects. So the global trajectory is correct in its way, because there aren't any moving objects. But for the local, there are kind of solutions that do this.
Thank you very much. Again, very interesting talk.
Thanks.